Well, good morning. It is a pleasure for me to introduce the talk of today by Jorge Sanchez Almeida. All of you know Jorge. He's a frequent assistant of these seminars, very active one. I must say this is one of the most dedicated scientists I know, for sure. And there are things of Jorge that some of you may not know. He has been working most of his life in solar physics. Fernando knows. And it was just 8 years ago that he decided to move to a different topic. In this sense, I am quite happy to have somehow contributed to convince you that the study of the formation and evolution of galaxies was a challenging and important thing to work on. And so Jorge started to do that, as I said, about 8 years ago. Since then, we have done a number of papers, and he has been leading most of them on a particular topic, which is very important, which has to do with the streaming metal-poor galaxies. Streaming metal-poor galaxies in the nearby universe are very important because we think they have the full size of the primitive universe, and because of that, they are excellent targets to do cosmology from nearby. As a result of this work, the summit has been that we have been invited to write an astronomy and astrophysics review that was just accepted 2 weeks ago, and is what Jorge is going to tell us today. So, Jorge, thank you very much. All for you.
Thank you for this kind introduction. And so I'm going to talk about today, what I'm going to talk about today is this, what is entitled, this star formation sustained by gas accretion. Star formation in this context is star formation in all galaxies in the whole universe, and gas accretion is accretion of metal-poor gas from the cosmic web. That's the global context. And as Cassiana has just said, this is a kind of summary of a preview paper that we have written for Astronomy and Astrophysics. And when I say we, I mean Deborah and Bruce Elmegren, Cassiana and myself. Now, it's a subject that is much broader than the type of things that we usually do. And therefore, we seek advice of many colleagues just from pointing out references to clarify points. And the list is simply too long to be given in detail. But I would like to mention two people, Daniel Severino and Claudio de la Vecchia, which has been critical for us to really understand. I mean, both of them are experts in numerical simulations of galaxy formation in this cosmological context, and they have been critical to allow us to dig into this wide and large literature on galaxy formation from numerical simulations, allow us to understand to some extent what is going on, and so to summarize it in the paper. So the presentation will try to follow these guidelines. I will start with I don't know whether I can, yes, I think it's going to work. So I will start with a kind of general introduction, and I'm going to show a couple of nice movies about these galaxies that have been formed in the universe, and also to try to explain the type of galaxies at which this review refers to. And then the next point is a kind of analytical description of why, that try to give physical insight of why gas accretion is so important at determining the galaxy stellar populations. Somehow it tells us what are the physical basis of something that comes out in the numerical simulation. So the next item, this one, expected properties, will try to summarize the actual properties that you derive from the numerical simulations of the gas that have been accreted by the galaxies that is forming in the end stars. Now, from this point on, so far I will talk about simulations. From that point on, I will talk about observational hints of this gas accretion and the role of this gas accretion. And there are many, as I will repeat more than once, there are many hints that actually gas accretion is playing a crucial role, none of which is sort of conclusive. I mean, the things are very clear from numerical simulations and also clear from observations. There are many hints. I'm not going to go through the whole list of hints that are mentioned in the paper. I'm just going to pick up examples, like examples of hints of accretion inferred from gas observations, from neutral and ionized gas, hints inferred from stellar observations, Scaling laws that I'm using this term to describe general properties followed not by individual objects, but the whole family of galaxies that are easy to explain if the star formation that we see is driven by gas accretion of metal poor gas. And this is what I will mention briefly here. And finally, I will conclude talking about gas accretion in a larger cosmological context, so basically the whole universe. Now, let me start by reading this sentence because I want to be precise, is that numerical simulations of galaxy formation predict that accretion of metal poor gas from the cosmic web fuels the star formation of these galaxies. Okay? This is something that happens at all redshifts, in the local universe and at high redshift. And there is a really very little dependence on redshift as far as the prediction of the model, of the numerical models is concerned. I will explain that there are two modes of gas accretion. One of them is the so-called cold flow accretion, and it's extremely efficient at transporting gas from the cosmic web to the galaxies where it is processed to form stars. And this mode, which, as I will argue, is the one that seems to be driving most of the star formation, is something that depends just on the mass of the dark matter halo that hosts the galaxy. And it's very independent of redshift. Or the dependence of redshift is through the mass of the dark matter halo that is hosting the galaxy. Now, the fact that this cold flow accretion or gas accretion is so important is obvious from a numerical, from a theoretical point of view, and it's not so clear from observations. As I mentioned before, there are lots of hints pointing in that direction, none of which is sort of the final hint of the final proof. Now, let me now start with a couple of movies which I find impressive. By the way, I wanted to show numerical simulations by Claudio, but I didn't. We didn't manage to make it run in my computer. So I'm using these other ones, which, by the way, are not so nice as the animations by Claudio, but they are very nice in any case. So the four panels, they show 100 megaparsec cubic volume that is evolving with redshift. You see there, this is stellar light, this is the gas density, this is the gas temperature, and this is metallicity. And I want you to see first how the gas is moving along the streams of the cosmic web to the nodes of the network. That is moving all the time. I also want you to notice how the metallicity, which were basically zero at high redshift, is increasing with time. And somehow the metals are ejected from the galaxies and are contaminated the whole intergalactic medium. Okay, things are going to be more clear as time goes on, or redshift decreases. Now we are at redshift 2. I'm not going to discuss the temperature, although it's very impressive. But in any case, the temperature is increasing where the stars have been formed, the temperature of the gas. And I want you to see how the gas keep falling in, the galaxies are being formed, and the metals are spread all over the place. Now, the second one is even more interesting from my point of view. This is a snapshot, so no time variation, and this is a flyby, the 3D volume, and this is the gas density of the network. Pressure 2, but the topology is similar to the topology that we have in the local universe. And I want you, this is gas density, okay? And what I want you to notice is how every disk, which is full of gas, is fed by streams of dense gas that end up in the disk. This is what numerical simulations are telling us, okay? So you have this network of gas spread out all over the place, forming filaments and nodes, and the filaments end up in the nodes where you are forming a galaxy. And the nodes of this cold gas is feeding the formation of the gas. So you can think of any concentration and you will find filaments that end up in the concentration. It's very clear in these two guys. You have one or two or even three filaments feeding them. So this is prediction from numerical simulations that try to be as realistic as possible. We can then at the end discuss whether this is realistic enough or not, but this is the prediction of the numerical simulations. Okay, let me finish here. Okay, so 2 points to define the framework. First is that what I'm going to discuss next refers to isolated galaxies, where you have a galaxy and the filaments of gas that are feeding them. So I'm not going to talk about dense environments like clusters of galaxies. So this I won't discuss, where you have also the interaction between galaxies playing a key role in the business. And because I'm dealing with isolated galaxies, I will also skip the issue of the satellite galaxies, which are strongly influenced by the gravitational pull of the galaxy that is there. So this refers to isolated galaxies. Actually, this is a term that I don't want to use. Actually, I want to avoid that. It does not refer to dense environments. Okay, so no clusters. Another important issue is that when people start talking about galaxy formation, often has in mind this paradigm where mergers of galaxies play a key role. It turns out that these mergers of galaxies are not so important as far as the stellar populations is concerned. If you take one of these numerical simulations and keep track, you have your galaxy at this, let's say, 0 redshift, and you keep track of the origin of the stars that you have in your galaxy. Most of them were formed in situ from the gas that is accreted, are not stars that were from elsewhere and somehow, by merger, end up in the galaxy. So mergers are really secondary. This 20% is actually an upper limit because this number comes from the whole numerical simulation that includes these dense environments where these processes are far more important. So mergers are not so important. Now, I pointed out this when I started, and basically there are two modes of gas accretion. The traditional one, so to say, is a hot gas accretion. It works more or less as follows. So you have your gravitational potential, and you have the stream of cosmic gas that falls in. As it falls in, by gravitation acceleration, it increases speed to a point that it exceeds the sound speeds of the medium, and it gets shocked. So it gets heated. And when it is heated, the temperature is so high that the time scale for the gas to cool down is longer than the age of the universe, basically. So you basically create a kind of halo of hot gas. This is what was originally expected to happen. And like 10 years ago or so, Decker and Greenboy pointed out that this was the process that was expected to happen when the halo was massive. When the halos are not so massive, then the temperature of the shocked gas is not so high and the density is higher, so that the cooling time is much shorter, and somehow this shock that is created naturally when the gas comes into the dark matter halo loses its pressure support, and it's sort of displaced down to the center of the gravitational potential. And basically, it's as if the gas from the cosmic wave were coming directly by free fall into the center of the gravitational potential. This is the cold flow mode of gas accretion. Well, it turns out that, as I mentioned at the beginning, whether you are in one or another depends on the mass of the halo, basically. So if the halo exceeds these 10 to the 12 solar masses, which is slightly lower than the Milky Way at the present time, then if it exceeds this threshold, then it's the hot mode of gas accretion, the one that dominates. And if it's below this threshold, it is the cold flow accretion that dominates. Now, Fernando is going to ask something. I will mention that kind of thing. So we are talking for the cold is a few times 10 to the 4 Kelvin, and for the hot is well above 10 to the 6. Okay. I mean, this paper, maybe you would like that, I think. It's a very, I mean, it's very theoretical, a very order of magnitude thing, which turned out to be confirmed by numerical experiments, so to say. Well, the point I was mentioning is that this redshift is not so important in this business. It's just the mass of the halo that determines whether you are in the hot or the cold mode. And now, this means that dwarf galaxies in the local universe, all of them are accreting through this cold flow, and all galaxies are high redshift, because remember that the mass of the halo are built up with redshift. So all galaxies were below this 10 to the 12 solar masses are redshift like 3 or 4. Even the progenitors of the massive galaxies that we see today, that are produced by mergers of galaxies, come from galaxies that grew through this cold flow accretion. So it's very important for all galaxies at high redshift, and important for galaxies below, slightly below the Milky Way size in the local universe. Another property of this gas accretion is the fact that it's very, very bursty. These 4 panels show 4 galaxies, and the accretion rate with time, we are here. And so this is the origin of the universe. And the mass increases, so this is the one of lowest mass, and increases this other way. So these are massive galaxies, a low mass galaxy. And this blue line shows the gas accretion rate in this cold flow mode. And you see that it's very bursty. And there is no hot gas being accreted in this dwarf galaxy, basically. Whereas if you go to a galaxy which is super Milky Way, so to say, it is the hot mode, the one that dominates. Again, this is from numerical simulations. So these numerical simulations predict that the gas accretion rate actually determines the star formation rate of the galaxy. So if you feed your galaxy with 1 solar mass per year, you get stars more or less at that rate. And I will explain why this happened using a simple analytical model. Now, everything can be pinned down to the so-called Koenig-Schmidt law, or things that are close to the Koenig-Schmidt law. This is an empirical law that tells that the star formation rate of a galaxy that you measure somewhere is something that scales with the mass of gas, of neutral gas that is ready to form stars. So there are various ways in which you can write down this law, but at the end, that's what they are telling. So it tells that the star formation rate is proportional to the mass of gas that you have ready to form stars, okay? And empirically tells you the time scale to transform all that gas into stars. So the star formation rate is proportional to the mass of gas that you have to form stars with a time scale which is set by observations and is very short. It's of the order of 1 gigayear in this context. This is very short for a cosmological evolution of a galaxy. So the fact that this time is so short is what determines why the cold flow is so important. The gas accretion is so important in all this business. It's like if you put gas in the center of a gravitational potential, in 0 time, it is transformed into stars. That's what it says, 0 time in a cosmological context. And so if you have gas, it is because it has just arrived from outside. Otherwise, it would be transformed into stars. Now, suppose that you are in the simplest world, and so your galaxy just have 2 components. They have stars and gas. And you can write down a mass conservation equation, which is the type of mass conservation equation that you get in chemical evolution models. So that the variation of the gas is decreased because you are having stars, and increased because you have gas inflow and gas outflows. Okay? Now, this R here is just the return fraction, so it's the gas that is returned by star to the interstellar medium in form of winds or supernova explosions and all these kind of things. The inflow rate is the gas that is provided by the cosmic web, and the outflow is parameterized in this other way. So the outflow are proportional to the star formation rate. This makes sense because the outflows are produced. These are, by the way, outflows at a galactic scale. So it's gas that escapes from the gravitational potential of the galaxy. So it's not a tiny thing. It's something that really goes back to the intergalactic medium. Well, the forces that drive these outflows are star formation. It's supernova ejecta, stellar winds, even AGNs somehow can be connected with the star formation rate. So it makes sense to parameterize it in this way. Now, the star formation rate, because of the Koenig-Schmidt law, scales with the mass of gas. So this is actually a first-order linear differential equation, easy to solve. And so this is the solution. And because of the time scales is so short, this exponential here is just like delta functions. So in the end, in this limit, it turns out that the star formation rate is something that scales with the inflow rate. So if you double the inflow rate of gas, you double the star formation rate. If you zero the inflow rate, you zero the star formation rate. Okay? And it is only due to the fact that this not necessarily. The only key ingredient is that this time scale is short compared with a typical time scale of evolution of the medium. And the gas consumption time scale, which is of the order of 1 gigayear now, decreases, actually scales with the Hubble time. So it decreases with time. So, yes. Yeah, but even from observations, even from observations, we know that it decreases. So there are a couple of observational papers measuring at redshift 1 or 2 or something like that, and it's like 1/3 of this 1 gigayear that's the number that I have in mind. So, but the critical point is not so much whether this number is large or small, it's whether this number is small compared with the time scale at which things vary in the galaxies. Okay. And if that is the case, then you enter in this kind of quasi-stationary state where the star formation is basically driven by the inflow gas. Now, you can keep with this simple model and do a couple of additional things. First is write down the mass of gas, which again is proportional to the inflow rate. And so if you zero the inflow rate, you have no gas in your galaxy. So it's basically the inflow rate that determines the gas that the galaxy has. And it works the following way. The inflow rate determines the star formation rate that you have in your galaxy. And so the gas that the galaxy has is that which, according to the Koenig-Schmidt law, produces that star formation rate. So it's a self-regulated process, so to say. So the gas is the gas that, according to the Koenig-Schmidt law, is needed to maintain the star formation rate that is driven by gas inflow. Now, if you make this following game of separating the gas that you have in a gas that has been processed by stars in the galaxy and gas that has come from outside, and you work out what is the ratio between the star formation rate of this external gas and the total star formation rate, it's always of the order of 1. So the basic idea is that in every starburst that you see at high redshift or the local universe, most of the gas is gas that has just come from the cosmic wave, just meaning in a time scale of 1 gigayear or so. And it has never been processed by the stars in that galaxy. You can write down an equation also for the metallicity, and there is another very, originally unintuitive result, but if you think a little bit about that, it becomes intuitive. And it is the fact that the metallicity of the gas that is forming stars is the metallicity of the inflow gas, but it's basically 0 because this is metal pool. Plus something that basically depends on the stellar physics, and is independent on the inflow rate, the gas mass, and blah, blah, blah. So the metallicity of the gas, if you think that the stellar evolution processes of all the galaxies are the same, and you assume that the mass loading factor of the galaxies are basically the same, the metallicity of all the galaxies should be the same, independently of the gas accretion rate. Now, I'm not going to try to explain how this happened, but the point is that we know observationally that that is not the case. So different galaxies have different metallicities. How it happened? Well, this is the yield. By the way, I didn't mention this fact, but this is the fraction of metals that are produced by stellar generation, one generation of stars, basically. And this is the return fraction. So these are things that should be the same in all galaxies, basically, unless you start changing the initial mass function, these kind of things. And the only other thing that you can play with is this mass loading factor. And remember that is the scaling between the star formation rate and the outflows of the galaxy. And for this guy to play an important role, so for this galaxy to dominate, the metallicity has to be very large, of order 1 or larger. So if you want your galaxies, if you want galaxies of different masses to have different metallicities, as it is observed, then the mass loading factor has to be very, very large, of order 1. So if you throw one solar mass, you transform, let's say you throw one solar mass, you produce one, let's say, half a solar mass, and another half a solar mass, you throw it back to the intergalactic medium. So in a very, very inefficient process. That's the bottom line. Now, so far, I finished with the simple model, and I will now talk about actual predictions. So the properties to be expected from this accreted gas. First, it has to have low temperatures, meaning this few times 10 to the 4 Kelvin, which at these low temperatures is low enough to maintain the hydrogen in a neutral phase. So this is neutral, or it contains a lot of neutral hydrogen. You expect that the gas that is accreted is falling in, although even if this is a very clear prediction, it's very hard to check observationally, because it's very hard to we have just the Doppler shift that tells us about relative motion. So you never know where something is just having a proper motion with respect to something else, is falling in or is going out. It's low metallicity. I mentioned that, well, it's pristine. Originally, a high redshift is pristine gas. And so it has to be low metallicity all over the time evolution of the universe. But remember that you have these outflows that are contaminating the intergalactic medium with metals that are produced by the galaxy. So even if it is low metallicity, the metallicity is going to change with redshift. And in the local universe, the prediction is that it's going to be of the order of 1% or so. Solar. There's plenty of dense neutral gas around the galaxies. So you expect that if you manage to observe an intense source, a background source, it will produce absorption in the spectrum of this background source. So if it is neutral, it will be in the base state of the hydrogen. So you expect that it absorbs Lyman alpha photons. So you expect that if you have high redshift quasars, the spectrum will be sort of absorbed by Lyman alpha photons absorbed by these intervening clouds of the cosmic wave. It's a gas, again, that is at these temperatures, has its density, so it will undergo recombination, it will produce light, it will scatter light from the UV background, for instance. So you expect also that the cosmic wave shows up in emission somehow. And again, because of the importance of this mass loading factor, you also expect to see outflows from the galaxies. This is a prediction. Now, this is a general prediction, and this is a specific prediction made by Van der Voort and Chaillet in this recent paper. Here are various physical properties represented versus the distance to the center of the gravitational potential. So this is the center where the galaxy is, and this is the virial radius of the dark matter halo. Now, the virial, from a physical point of view, the virial radius is the distance at which, the gravitational influence of the dark matter halo starts to be dominant, so to say, for the matter that is around there. And this virial radius is something which is very large compared with the typical optical radius, let's say the half-light radius that we all are used to deal with. So it's maybe 100 times larger. Okay, so this is a physical property, how it varies with the distance to the center of the gravitational potential, and the galaxy is something tiny here. That's what I was trying to say. Now, I just want to point out two things. These two colors, this pink and green, represents this hot. By the way, this is a redshift 0 Milky Way halos, where more or less this hot and cold gas accretion are happening more or less at the same, not at the same rate, but they have more or less the same importance, at least in terms of mass. I will point it out. So you have gas that is hot, which is this gas here, and gas that is cold. This is 10 to the 4, 10 to the 6. Okay. What else? The metallicity. The metallicities here are around, this is solar, 1/10, 100 solar. Of the cold component is of the order of, 100 or so. Now, the inflow rates at the virial radius are, this is a logarithm scale, solar masses per year, and so the inflow rates are about here. So these are 2, 3, 4, 5 solar masses per year for Milky Way halos. That's the inflow rate that is predicted. And also the velocities, the inflow velocities are of the order of 100 kilometers. So they are not very large. Again, this is another piece taken from numerical simulations. Fumagalli et al. Did the rate transfer needed to determine from a numerical simulation what is the amount of neutral gas that you have there, which is something that you can compare with the observations. And what they found, by the way, these are different galaxies at different redshifts. This is redshift 4, redshift 1. And what you have in color coded, by the way, these circles there are the virial radius, these radius that more or less determine what is the gravitational influence of the dark matter halo. And what is color coded is the hydrogen column density. And the point that I want to make here is first that things are denser at higher redshift, so the cosmic wave becomes less dense as you approach to the local universe. And the column densities are those that we now associate with Lyman alpha system or Lyman limit system. This is a prediction from the numerical simulations. Now, I finished now with the numerical simulations, and I'm going to start talking about the observations. So there's no water, right? No, that's fine. That's fine. I will survive. So starting with observations. And I mentioned at the beginning that there are many evidences, and we'll just pick up a few of them that seems to be representative of the whole set of evidences. The first one is accretion that's inferred from neutral gas observation. We all know that if you, with our radio telescope, you observe these 21 centimeters of hydrogen, and the whole universe is full of hydrogen. A significant part of that is actually gas that's been accreted by the galaxies. There are cases where this thing is extreme, like the one that I'm going to show here. This galaxy is 1318. It's one extremely metal-poor galaxy. That is forming stars, I was going to say like hell, a lot in the local universe. This is a dwarf galaxy, so in absolute terms it's not so large, but for the mass of the galaxies, it's like having the whole galaxies going crazy forming stars. And now the image of the galaxy, by the way, this is the image of the galaxy is here, and this square here is actually a zoom of this region there. And the contour lines here represents the amount of hydrogen that you have. The mass of hydrogen of these galaxies is like 10 times the mass, the stellar mass that you have. So it's a large amount of gas that surrounds these galaxies that it produces stars a lot. Now, the point that I want to make is that if you measure the velocity, if you measure the velocity field of the galaxy, you see a rotation, very clear, associated with the galaxy. And then there is a plume of gas that is like ballistically going into the galaxy. This is very suggestive, okay? And this is not an sort of exceptional case. There are many cases of very distorted H1 morphologies that somehow hints at these streams of gas that are falling into the regions where stars are being formed. Now, a second thing is hints obtained from H2, from ionized gas, and now I'm going to mention it's actually our connection with this field, that the origin of our interest for this cold flow accretion. Now, if you select galaxies that are extremely metal poor as you can in the local universe, they tend to have a number of properties that are very unexpected. The first one is that they turn out to be cometary. So you want galaxies which are metal poor meaning a metallicity lower than 1/10 the solar value. The gas that is forming stars now, these are rare galaxies and they turn out to be cometary. It was very strange. We think we understand now why this happened. But what I'm going to discuss next is that among these properties, the fact that they are cometary or tadpole, they have a distribution of metallicity which is highly inhomogeneous. So you have your galaxy like that. You have a bright head and a tail. And it turns out that the metallicity of this bright head, that is a Gaian H2 region, so it's forming stars a lot, is much lower than the metallicity of the rest of the galaxy. These are disks that are rotating, this you can measure, and this head, which is forming a star, is offset with respect to the center of rotation of the galaxy. So this is very hard to understand because the mixing time scale of the gas is pretty short. It's of the order of the rotation time scale. And so if you see a chunk of gas producing stars with very low metallicity, it has just arrived. And this is very suggestive of gas that has been recently accreted from the intergalactic, from the cosmic wave, basically. Now, you have this association between a very strong star formation and low metallicity in these particular galaxies, which are hard to explain in general and kind of naturally produced if these galaxies have just received a big chunk of gas that is almost ready to form a star, and so it's starting to form a star, and it's a low metallicity gas. That's why the metallicity of the gas that is forming stars is much lower than the metallicity of the underlying galaxy. Now, let me move on into the next item, which is accretion inferred from stellar observations. And I'm going to discuss two things. The first one are the so-called polar ring galaxies. Polar ring galaxies these are two examples of polar ring galaxies. They are an early type galaxy, is this red thing here. This is the galaxy. So this is the polar ring. So the real galaxy is this thing here. And usually it's a massive old galaxy. And it has this ring of galaxies perpendicular. So it's a kind of extreme case that is blue because it's forming stars now. And this is measured to be gas-rich. And the stellar populations are very, very young of these rings. So the way to understand this is because the galaxy, the old galaxy, has received a stream of gas, or maybe a satellite, a gas-rich satellite with few stars in that particular polar orbit, and that's what we see as a polar ring galaxy. Okay, so it's gas that has just arrived onto a galaxy that was there for long. Now, the second hint that I'm going to mention is the so-called G-dwarf problems, and I'm choosing this for at least two reasons. These G-dwarfs are not dwarf galaxies, they are dwarf stars. Okay? And I'm choosing this problem for two reasons. The first one is because, so far as I'm aware, is the first observational evidence that you need to understand the observations. You need the contribution of large, systematic gas inflow. Otherwise, it's very difficult to explain. And the second thing is that it might be relevant for people that are studying things like variations of metallicity across the galaxies and metallicity variations with time. Okay? So the G-dwarf problems date back to the 60s of the previous century, and it rephrased in a way that we can understand now. It's kind of summarized in this plot. But before I go to the plot, let me tell you what is the intuitive idea that you should have if you have a chunk of gas, you start to form stars. And this gas is isolated, so it's a closed box. So you have the gas, you form a first generation of stars, you eject some metal, forms a second generation of stars, and so on and so forth. So the first generation of stars is metal poor, because this is metal poor gas, and it's very massive. Okay? The second time you have less gas, more metallic. So you have less stars, which are more metallic, and so on and so forth. So you expect an increase of the metallicity of the stars that are informed with time, and a decrease of the number of stars that you have in this closed box evolution of a chunk of gas. Okay? Now, if you measure in the solar neighborhood the metallicity of the G dwarfs, which are long-lived stars, so you don't have to pay attention about this star being, dying, this kind of thing, you get the following thing. This is the number of stars that you have, and this is the metallicity in a weird scale. But this is a linear, it's strange, because this is a linear scale of metallicity, which should be the natural one, but we are also always using this logarithm scale. So this is solar metallicity, and this is sub-solar metallicity. Lines are different models, and the real observations are these points here and these crosses. And the point is that around solar metal, most of the G dwarfs are around solar metallicity. There are very, very little low metallicity stars. So this is very hard to reconcile with this closed box evolution. And how, there are many interpretations. People have been, there are literally hundreds of papers trying to explain this thing. But so far as I'm aware, the explanation that is commonly accepted is one that was proposed long ago by Larson and had to do with this equation that we mentioned in the simple model. It's basically the fact that when you are in stationary state, you're feeding your system with gas, and you reach this stationary state, the metallicity of the gas is fixed, it's constant, it doesn't change with time, because it's regulated by, maybe I was saying that, okay, let me try to explain how this works. You have your system that is forming stars, and you are feeding it with gas. So you are producing new stars from that gas. And so in producing new stars, you are taking out part of the metals that this gas had. And those metals you put into long-lived stars. And so you are sort of hiding, you are removing part of the metals from the gas. At the same time, you have this massive star that returns metals to the medium. In the stationary state, the gas that you put into long-lived stars, the metals that you put into the long-lived stars, the same amount of metal that you return to the medium by young stars. And that's why you reach this stationary state. But the point is that if you are in that stage, which I have been arguing that's the natural state for the disk galaxy to be in that stage, the metallicity of the gas is going to be constant. It's not going to vary with time. And therefore, all the different stellar populations will have that metallicity. And which one is that metallicity? If you work out the numbers, basically that metallicity is given by the yield, which is the solar metallicity. So you expect, actually, that in this stationary state, your different stellar population will have the solar metallicity. Actually, then the dwarf problem is not a lack of low metallicity stars, but actually it's an excess of solar metallicity stars, because the gas has been regulated, has been tuned to have always the same metallicity. Now, let me move on into our next point, which is this scaling laws. As I pointed out when I was going through the list of items, there are properties, general properties that are followed not by individual targets, as I have been mentioned in this case. The last one was the Milky Way. I show a couple of examples of these ring galaxies and with these dwarfs. But there are properties that are followed by the vast majority of the galaxies. And so whatever the explanation is something that has to be fundamental, because it affects not just one galaxy, but many. And actually, these scaling laws are laws that relate different physical properties that can be measured of the galaxies. There are many of those laws, I have listed them here, I'm not going to go through them, that can be naturally explained if a star formation is driven by gas accretion. I will concentrate on the last one, which is the relationship between the stellar mass of a galaxy, the gas metallicity, and the star formation rate at present of that galaxy, which is in the jargon called fundamental